Higher education is undergoing a difficult transition. The modern university is no longer expected to simply broadcast information. It must guarantee deep, structural learning. This creates what we can call the professor's paradox. A university instructor, possessing immense domain expertise, delivers a brilliant, logically sound lecture. Yet that flawless delivery rarely translates into stable, usable knowledge for the students in the room. To understand why this breakdown occurs, we have to look at John Sweller's cognitive load theory. Sweller separates human knowledge into two categories. We have biologically primary knowledge, like basic social interaction, which we acquire naturally. Then we have biologically secondary knowledge, like higher mathematics or law. This secondary knowledge requires deliberate instruction and taxes our cognitive architecture. This split screen illustrates the exact structural difference between an expert and a novice. On the left, the professor possesses massive, organized cognitive schemas in their long-term memory, allowing for instant pattern recognition. On the right, the student relies on their working memory to process new information. That working memory is strictly limited, capable of holding only about 4 distinct elements at a time. When a professor casually explains a multidimensional concept during a traditional lecture, a rapid influx of new variables hits the student. The limited working memory slots immediately overflow, and the excess data simply vanishes. The traditional lecture format structurally generates extraneous cognitive load. Overcoming this requires abandoning intuitive teaching methods and replacing them with engineered educational design. Long before cognitive load theory was formalized, Soviet psychologist Pyotr Yakovlevich Galperin engineered a deeply pragmatic solution to this bottleneck. He developed the theory of stage-by-stage formation of mental actions. The standard educational paradigm places the instructor as an observer, watching students use trial and error, hoping a new psychological process spontaneously emerges. Galperin argued that this passivity guarantees the formation of flawed cognitive habits. His methodology bypasses the working memory bottleneck entirely. Instead of forcing a student to juggle complex, abstract variables entirely in their head, Galperin's system extracts the professor's internal expert schema and externalizes it into the physical environment. By placing the logical structure of a problem on a physical page or screen, that external schema acts as a temporary hard drive. The student's working memory is completely relieved of the burden of holding the problem's architecture, allowing them to focus 100% of their cognitive effort on executing the action. Professional expertise is not the result of sudden inspiration. It is a highly specific physical action that is actively driven from an external, material state into an internal, mental state. The foundation of this system is the orienting basis of action, or the OBA. This is the precise structural map a student uses to understand the goals, plans, and means of solving a specific problem. This diagram shows 2 approaches to that map. Traditional professional training often relies on a Type 2 orientation, teaching a rigid step-by-step algorithm for a specific task. But in an economy where technological development rapidly outpaces curriculum updates, those rigid algorithms become obsolete before the student even graduates. Galperin's solution for higher education is the Type 3 orienting basis of action. Instead of teaching a disposable algorithm, the instructor trains students to identify the invariants of a discipline. Invariants are the fundamental, unchangeable structural laws of a system that remain constant no matter how much the surface variables fluctuate. You see invariants across all hard and social sciences. In mathematics, a triangle's area is invariant with respect to the isometries of a Euclidean plane. In law, the composition of a legal offense, object, subject, objective side, subjective side, remains identical whether prosecuting a 19th century theft or a modern cryptocurrency fraud. Albert Einstein relied heavily on invariant logic, resolving the long-standing conflict between electromagnetism and classical mechanics by anchoring his special theory of relativity on a single invariant. The speed of light in a vacuum remains constant for any inertial observer. Designing a Type 3 orientation requires the professor to strip away secondary facts and isolate the genetic core of their subject. Doing so gives students the structural framework to solve completely novel problems they haven't encountered before. This animated timeline outlines Galperin's 6-stage pipeline. This sequence is the mechanism used to translate that external invariant matrix into an automated, integrated neural pattern. In Stage 1, the instructor creates a motivation deficit by presenting a professional problem the students cannot solve with their current knowledge. In Stage 2, the instructor delivers the orienting basis of action, the comprehensive physical map containing all the discipline's invariants. Stage 3 is the materialized action. Students solve problems by physically interacting with the external schema. They trace the logic with a finger or stylus. This physical reliance strictly prohibits the student from attempting to solve the problem in their head, completely protecting their working memory from overload. In Stages 4 and 5, the physical schema is taken away. The student now uses external articulated speech to carry the action. They must verbally state every logical step. As proficiency increases, this loud speech condenses down into whispers, and eventually into internal soundless speech. By Stage 6, the action transitions fully into the purely mental realm. The process becomes completely automated and instantaneous. The student looks at a complex problem and instantly intuits the structural solution without consciously registering the intermediate steps. When an educational program skips the physical and verbal stages, expecting students to jump straight from hearing a lecture to performing mental operations, high failure rates are the mathematical certainty. Let's examine how this theory dictates the microarchitecture of a specific university class. Take a 2-hour civil law seminar on invalidating contracts. Instead of a traditional pop quiz, the professor spends the first 15 minutes in the orientation phase. The instructor distributes the Type 3 orientation matrix. This document visually maps the invariant logic of contract flaws of subject, will, form, or content. During the 35-minute materialized action phase, students receive case files. Intuitive guessing is strictly forbidden. They must physically fill out the matrix, routing the facts of the case through the specific branches of the invariant algorithm. In the loud speech phase, the physical matrices are confiscated. Students are paired up. One student must verbally articulate every logical step of the contract analysis aloud, reconstructing the matrix from memory, while the second student audits their logic. The seminar concludes with the mental action phase. The professor initiates a rapid-fire digital test. Students have exactly 20 seconds per case. Speaking and drawing are prohibited. The time limit forces the brain to abandon intermediate verbal steps, relying entirely on the newly formed instantaneous neural response. Applying this specific architecture to a seminar replaces the usual chaos of confused students with a systematic, observable progression of skill. The resulting knowledge is highly transferable to new contexts. Implementing this framework in modern academia often meets a specific critique. Critics suggest that strictly managing a student's cognitive progression through invariant stages stifles creativity and produces rigid executors. This critique misinterprets Type 3 learning. Mastering invariants does not mean memorizing a rigid template. It means the student has successfully acquired the universal meta-language of their profession. We see this principle in high-level performance anywhere. A jazz musician cannot successfully improvise a solo until they have fully automated their understanding of scales and harmonic invariants. True creative freedom in a discipline only begins after the foundational orientation is flawless. Galperin's methodology provides the exact cognitive infrastructure required for a student to reach the highest levels of Bloom's taxonomy, giving them the tools to evaluate theories and synthesize novel ideas. This diagram illustrates how the framework operates across a diverse cohort. A traditional lecture inherently filters out students with smaller working memory capacities or attention deficits. By utilizing the orienting basis of action as a structural bridge, students of all capacities can process the data and reach the exact same expert schema. Externalizing the cognitive load is a direct application of universal design for learning. It levels the playing field, ensuring academic success for the majority of the room without ever having to lower the rigor of the material. For the modern professor, this requires an operational pivot. They must step away from the role of content transmitter and adopt the role of a cognitive engineer. By managing cognitive load and actively guiding students through the physical and verbal stages of invariant structures, universities can fulfill their primary function, deliberately mass-producing highly adaptable, deeply motivated professional minds.